Hi, in this video, I will present the variation of parameters method for finding a particular solution to a non-homogeneous second-order differential equation. Now, variation of parameters is actually a very powerful method that can be used for higher-order differential equations as well. So what I want you to get out of this is not just a formula or something, right? I want you to understand the general idea of variation of parameters so that later on in your career, either in a higher level course, or as a working professional, if you run into variation parameters when it comes up in other contexts, you will understand what's going on.
The version you see in this class is for a non-homogeneous, second-order, linear equation with constant coefficients. And we use it to find the y sub p. But variation of parameters is actually very powerful. You can use it to find a particular solution y sub p for other situations as well. It works for higher order, and it works for coefficients that may not be constants, that may be functions of t. Right, so let's look at an example. Find a particular solution to the equation y double prime plus y is equal to secant of t. This equation you cannot use undetermined coefficients because the non-homogeneous side here is not of the type that works with undetermined coefficients. Remember that for undetermined coefficient, the non-homogeneous side has to be some product or sum of polynomials or exponentials or sine cosine. This is none of the above. You may say that secant is 1 over cosine, and that's true, but there isn't an undetermined coefficient method for 1 over something. You may also say, what if we multiply both sides by cosine? That's actually a good idea most of the time. So let's try it. We get cosine t y double prime plus cosine t y equals 1. That looks fine, but no undetermined coefficients here either because the equation has a non-constant coefficient. Well, it has two non-constant coefficients, so we need a new method. In general, let's say we're given the equation a y double prime plus by prime plus cy equals a function of t. I'll call it f1. First thing is I'll divide both sides by a. So y double prime plus b over a y prime plus c over a equals f1 of t over a. And by the way, a, b, and c can be functions of t. They don't have to be constants. So already this method is more powerful than undetermined coefficients. I divide it by a because I like to have the leading coefficient here just equal to 1. Then I call this p. P can be a function of t. And I call this q. And on the right-hand side, I call this f. So the form of the equation is y double prime plus py prime plus qy is equal to f of t. So let's number this equation 1. Whenever we have a non-homogeneous equation, we always want to start out with solving the homogeneous version. So suppose somehow I know how to solve the homogeneous version, then I do that and I get two linearly independent solutions y1 and y2. y1 double prime plus py1 prime plus qy1 equals 0. And the same thing with y2. Box this up, number it equation 2. And the general solution of the homogeneous version of the equation is y sub h for homogeneous, equals c1y1 plus c2y2, where c1 and c2 are some constants. Now I'll go look for one particular solution, y sub p, to the non-homogeneous version. Here's the big main idea of variation of parameters. I'm going to speculate that maybe y sub p has a similar form to y sub h. Similar, yes, but not identical, because if it were identical, plugging in, I'd get 0 and never the f on the right-hand side. No matter what constant c1, c2 I use, I'll always just get 0. Well then fine, I won't use constant c1, c2. I'll use some functions of t instead of constants. So I speculate that my y sub p is going to be equal to some u1, y1 plus u2, y2, where u1 and u2 are functions of t. That's my big idea, so I'll box this up and number it equation 3. I'll put the number 3 over here. This is also where the name of the method comes from. It's called variation of parameters because I take the parameter c1, c2 and I turn it into something that varies with t. Hence, variation of parameters. Now the task is to find u1 and u2. Since I already know y1, y2, if I can find u1, u2, then I'll get my y sub p. Since y sub p is supposed to be a solution to the non-homogeneous equation, if I plug in yp and yp prime and yp double prime, it should work out, right? Okay, fine. So let's compute yp prime and yp double prime. To compute yp prime, I need to use the product rule. Yp prime equals u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. I'm going to gather all the derivatives of y1, y2 together. So y1 prime, y2 prime. And all the non-derivatives y1, y2 together. I can look ahead, I can tell that if I keep all of these terms, then yp double prime will be horribly long with lots of terms. So I tell myself, I'm making guesses anyway. Why am I making life hard? Since I'm guessing anyway, make the guess easy on myself. I'd like to keep only the y1, y2 prime, not the plain y1, y2. So I'll pretend that by sheer luck, these two terms right here add to 0. I want u1 and u2 to be such that the terms with plain y1 and y2 will go away. And I keep only the y1 prime and y2 prime terms. In other words, I want u1 prime y1 plus u2 prime y2 equal 0. That would simplify yp prime. Nice. I'm going to box this up. I'll number it equation 4. And this one is equation 5. All right. I still need yp double prime, so I differentiate again. Products rule again. Yp double prime is equal to u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime plus u2 y2 double prime. I gather all the y double prime together and all the y single prime together, and I get this, which I call equation 6. All right, this next step, I'm going to try to simplify this. I'm going all the way back to equation 2. These two equations, number 2. These define y1 and y2 as the homogeneous solutions. So from these, I'm going to isolate the second derivatives so that I can plug them into equation 6. So what I get is y1 double prime is equal to negative p y1 prime minus q y1. Same thing with y2 double prime. And I want to plug these into equation 6. So I need u1 y1 double prime and u2 y2 double prime. Right, so I'm going to multiply both sides of this equation by u1 and multiply both sides of this equation by u2. So I have these terms that look like the terms in equation 6. Okay, so I have u1 y1 double prime, and the other equation u2 y2 double prime, and in order to get a form like equation 6, I want to add these two equations together side by side. So on the left I have u1 y1 double prime plus u2 y2 double prime. On the right I have, let me group all the p's together and all the q's together. Now look at this. Have I seen this before? u1 y1 prime plus u2 y2 prime? Yes, I have. Here it is. This bracket is equal to yp prime because of equation 5. How about this other bracket? Here it is. It is equal to yp because of equation 3. All right, let me make this plus sign clearer. All right, so this whole thing is equal to negative p yp prime minus qyp. And all this is u1 y1 double prime plus u2 y2 double prime, which is this block here. So I'm going to plug back in for yp double prime in equation 6. So yp double prime is equal to that block. So negative p yp prime minus qyp plus u1 prime y1 prime plus u2 prime y2 prime. Move these to the left side. And you recognize this, right? This is the original equation. And if yp is a particular solution, then it's all supposed to be equal to f of t. So this whole thing is equal to f of t. I'm going to box this up. And now I'm up to equation number 7. All right, so check this out. I have this equation 4 It has u1 prime and u2 prime in it. And then I have this equation that also has u1 prime and u2 prime in it. So if I put them together, then I get two equations in two unknowns where the unknowns are u1 prime and u2 prime. So this is from equation 4. And equation 7, I'll write it down here. Two equations in u1 prime and u2 prime. So I'm going to box this up in red because it's the most important part. Double box. Now make sure you understand that in this system, u1 prime and u2 prime are the unknowns. The rest are known. y1 and y2 are known because they came from solving the homogeneous equation. And therefore, y1 prime and y2 prime are also known by taking the derivative of y1 and y2. Now I solve this system. For theoretical purposes right now, I will use Cramer's rule. In practice, if you can solve using some other methods, then by all means do that. Cramer's rule says the solution is some determinant divided by another determinant. For u1 prime, the denominator will be y1, y2, then y1 prime, y2 prime. For the numerator, I replace the u1 prime column, so the determinant will be 0, y2, f, y2 prime, which is equal to just negative f, y2 on top, divided by this denominator, y1, y2, y1 prime, y2 prime. Now for u2 prime, determinant divided by determinant. Same denominator. Numerator, I'm replacing this column. So I have y1, 0, y1 prime f, which is equal to positive y1 times f on top divided by the same determinant in the bottom. So this determinant in the denominator, we will define a shorthand for it. It's called the Wronskian, named after the mathematician Wronski. Definition. The Wronskian of two functions f1, f2, where f1 and f2 are differentiable. And you can generalize this to more than two functions, by the way. W of f1 and f2 is defined as the determinant of f1, f2, f1 prime, f2 prime. If you have more functions, f3, f4, then you just keep writing f3 or 4 and then add more rows of higher derivatives to make it square. In this class, we'll stick to just two functions. With that definition of the Wronskian, I have u1 prime is equal to negative y2 times f divided by w, and u2 prime is equal to positive y1 times f divided by w. I integrate u1 prime and u2 prime, I'll get u1 and u2. So u1 is equal to the integral of negative y2f over w. And u2 is equal to the integral of positive y1f over w. Okay, so by the way, check out how the subscript alternate and how the signs are different. All right, I have everything. I have my u1, u2. I've always had my y1 and y2. So I have everything I need for my y sub p. y1 times this u1 plus y2 times this u2. So this whole thing is the particular solution I'm looking for. Now, some people just jump straight to this formula and compute y sub p. That's quick, but I don't recommend that because that's really hard to memorize this formula. And even if you have your open notes, it just feels like the whole thing fell down from the sky. I would strongly recommend that you start from back here instead, from this system. Start from this system, solve it for u1 prime and u2 prime, take the integral, and then write the yp. Alright, summary. Given the equation ay double prime plus by prime plus cy equals f1 of t. First, divide by a to get to y double prime plus py prime plus qy equals to f of t. Step 1. Solve the homogeneous equation for y1, y2 linearly independent. Step 2. Solve this system, the one I boxed in double red, for u1 prime and u2 prime. u1 prime y1 plus u2 prime y2 equals to 0. u1 prime y1 prime plus u2 prime y2 prime equals to f, or f1 over a if you didn't divide at the beginning. Step 3. Integrate. u1 equals integral of u1 prime, u2 equals integral of u2 prime. The plus c, just make it 0, because why not? Life is short. Finally, step 4. Y sub p is equal to u1 y1 plus u2 y2. There we go. That's the totality of the variation of parameters method. I'm going to leave this screen on for a couple seconds so that you can hit pause and take notes. Now we're going to do an example. We'll go back to the example that I started with at the beginning. Y double prime plus y is equal to secant of t. The leading coefficient is already 1, so I don't need to divide anything. Step 1, I'm going to solve the homogeneous version. Y double prime plus y equals 0. The auxiliary equation is r squared plus, or no, plus 1 is equal to 0. So that means r is equal to plus or minus I. That means y1 is sine t and y2 is cosine t. Second step, I'm going to set up my system. u1 prime y1 plus u2 prime y2 is equal to 0. u1 prime y1 prime plus u2 prime y2 prime is equal to f of t, or f1 over a, which in this case a is 1, so it doesn't make any difference. y1 equals sine t, y2 equals cosine t. y1 prime is going to be cosine t, and y2 prime is negative sine t. So the system becomes y1 is sine t u1 prime plus cosine t u2 prime equals 0. y1 prime is cosine t times u1 prime plus negative well, make it minus sine t u2 prime is equal to f of t, and f is secant t. I could use Cramer's rule, but I don't have to. I am going to do elimination. I want to eliminate this term. That will work really well because secant is 1 over cosine, so it's convenient if I multiply all of the second equation by cosine. And that means I want to multiply the first equation by sine so I can eliminate the u2 prime term. So I have sine squared u1 prime plus sine t cosine t u2 prime equals 0. And cosine squared u1 prime minus sine t cosine t u2 prime equals 1. Adding side by side, these cancel. 0 plus 1 equals 1. Over here, I factor out the u1 prime, sine squared plus cosine squared. That's convenient because that equals 1. u1 prime equals to 1, and that means u1 is equal to t. I have my u1. I'm going to substitute it into this one. It has a 0 on one side, so it's easier. u1 prime is 1, so I have sine t times 1 plus cosine t times u2 prime is equal to 0. That means u2 prime is equal to negative sine t over cosine t. And u2 will be the integral of that. I'll keep the minus sign like this because I already see the u substitution. This is u. This is gonna be du. The whole thing will be just du over u. The integral of du over u is ln. So ln of cosine t plus c, but I'll just make it 0. So u2 is equal to ln of the absolute value of cosine t. And so y sub p. Alright, by the way, make sure you don't just stop here, okay? A lot of people get so excited that they find u1 and u2. They just stop. Don't stop. You need y sub p. Y sub p is equal to u1 y1. That's t times sine t plus u2, that's ln cosine t, times y2, that's cosine t, and that's our particular solution. If the question asks for a general solution, then I can just write down the extra terms. This stuff plus c1y1 plus c2y2, I just add it on if I need to, if the question asks for it. Anyway, so that's how variation of parameters works. Hope that helps. Thanks for watching. Bye.